session and really enjoyed it. So I'm co-chair here, but I'll leave the work to Rickson, and I'll be working on the background, make sure everything runs smoothly. Rickson.
All right, thanks, Mari. So let's start our last session. Unfortunately, it's been a great time for the past 3 days, right? So the session is going to be the software and hardware section. And we'll start with Ted Huppert from University of Pittsburgh, who will be talking about recent additions to the NIRS toolbox.
All right, thank you, Rickson. Let me see if I can PowerPoint. All right, can everyone see my screen?
Yeah.
Okay. So what I was going to talk about is some of the recent advancements we've made to our open source MATLAB toolbox called the Brain Analyzer, or often refer to it as the NIRS toolbox because I'm not creative. So for those who don't know, a couple of years ago, we established this toolbox. It was written by a really great graduate student at the time, Jeff Barker. It's open source on both GitHub and Bitbucket. We mirror those two sites. And just kind of just a really brief, it's a object-oriented toolbox, which means that all objects like data classes and stuff like that are treated with methods like, you could say, raw.draw, and what that does is that draws the data. And so everything becomes self-contained, that it knows how to draw itself, it knows how to do its own stats, and it becomes a really nice way of keeping the bookkeeping. So this is just an example. This is a little pipeline where we load up the data, we draw it to make an image that looks like this over here, and then we run the stats model in 2 or 3 lines. We can bring in the data and completely do statistical analysis to give activation maps like this. So so we think it's a really nice framework that we've had and we've offered for a couple years now. And so what we've done in the last in this year, in 2020, while we were all on quarantine, is we've added a couple of new tools. And so I wanted to highlight those. And so one of the tools that we've added is the ability to account for things like head size and probe registration. So this is an example from a paper that we recently got published this month in Neurophotonics, where what we're looking at here is basically if we had a probe that was across the forehead on kids with different head sizes, what happens is the activity, I think this is maybe BA 10 or so, it changes which channels are being projected as the head size grows. Right. So in a kid with a small head, it might project a bunch of channels. In a kid with a bigger head, it might be fewer channels. And if we look at any one channel, what we end up with is almost a 4-fold change in the effect size as this activity moves in and out of the sensitivity for different for the channels. And we see peaks corresponding to as it moves in and out of the gyri and so on. And so what we came up with was a mathematical way of dealing with this in the context of regions of interest, where the idea is to formulate the null hypothesis. What is, I believe BA 46 is not involved in this task. That's my null hypothesis. And if that null hypothesis is we want to test that, what we do is we take the registration and the anatomy and the definition of what BA 46 is, we project it out into channel space to get a weight, a distribution of which channels would have seen this tapered weight, and then we test that directly as the weight of those channels in the region of interest. And so this allows us to actually define on an individual basis, based on registration, a region of interest statistical test for different regions. And so my grad student, Zui Tong, published this recently, where we showed that compared to kind of taking the nearest couple channels or so, we got a lot better statistical power and the ability to account for things like head size. One of the other things we've been working on recently is the addition of methods to deal with short separation. And so we recently, my postdoc, Hendrik Sentosa, published this paper that did a sensitivity specificity analysis to compare different methods. And what he ended up finding was, no surprise, including short separation is good if you have it available. And specifically putting it in the context of the GLM model is a lot better than using it as a pre-processing step. So when your stats know about this, because it's actually integrated into the GLM, you have better improvements in sensitivity specificity compared to pre-processing. Another thing that we've been working on is multimodal. So one of the things that's a newer feature in the toolbox is the ability to have analysis of EEG, MEG, and fMRI data in the exact same set of scripts, the exact same function calls. And so this is an example of using the toolbox to analyze not only EEG data, but multimodal EEG NIRS data, where we can actually put the data together and do fusion of the images to make statistical maps using both modalities. And finally, just some newer features that I've added just in the last month or so. We've started to get a lot of requests from people looking at things like ordinal variables, categorical variables as part of their GLM. So we've recently put those features in. We now support dynamic connectivity, looking at changes in resting state as a function of time and using that in linear models. We've introduced repeated measure statistical models. We've introduced gray box system ID methods for looking at things like cerebral oxygen metabolism and blood flow. And finally, a work in progress, we've started to try to look at the comparison of different methods for incorporating short separation into functional connectivity estimates, and kind of the best way to do that, which looks like it's a little bit different than how you deal with it as a GLM task-based. So that's what I have. Thank you.
Thanks, Ted. So I'll just remind everyone that you can post your questions on the chat. I guess Mari just sent the link to everyone on the chat here. So our next talk is going to be by Javier Andrew Perez from University of Essex. And he's going to talk about computational intelligence in FNIRS data analysis. Javier?
Hello, everyone. Just going to check whether you can see my screen. Is that okay?
Perfect.
Yeah, perfect. Great.
Yep.
So, well, I'm going to start my presentation straight away. Let's see. I'm just going to, let me share it again. Yeah, now this. Hello all, I'm Javier Andrew Perez from the Center of Computational Intelligence at the University of Essex in United Kingdom. And I'm part of a multidisciplinary team doing research in the emerging field of computational cognitive neuroscience, which main goal is understanding how humans develop their cognitive abilities, while these help us to design a more nature-inspired artificial intelligence. Yesterday, there was an interesting session chaired by Professor Pepe Dan that discussed novel methods powered by artificial intelligence. In my perception, these methods can play a major role for applications requiring to model naturalistic observations such as neuroergonomics, developmental cognitive neuroscience, or applications that pursue ecological validity, such as, for instance, the project of Dr. Felipe Orihuela Espina of using FNIRS in rural communities. I would like to say that the field of machine learning is only a subfield of artificial intelligence. Overall, the whole domain can give us much more play. I'm going to show you a few quick examples about how our group is utilizing AI in different forms. This is an example of how to use artificial intelligence synthetic, highly noisy F-near hemodynamic signals, which contain effective information transfer between these channels. We found that the reconstruction error of the original signal in comparison with other state-of-the-art, such as autoregressive models and dynamic causal modeling, was much lower. And also, the method was able to decode the significant effective connections between channels with much better reliability than granular causality. Looking into a real problem of naturalistic studies with F-nears for modeling surgeons' proficiency, we found that the decoded effective networks for manual motor task proficiency were highly correlated and congruent with the previous studies of ROI integration in this field. This is very encouraging for a plug-and-play, purely data-driven design-agnostic method that only requires a minimal set of hyperparameters. Another investigations we are doing are in the impact that artificial intelligence might have in developmental cognitive neuroscience analysis. This is a field that is hampered by several limitations. This is a work that we are doing in collaboration with Professor Lauren Emberson. The idea here is using artificial intelligence to empower a highly flexible and sensitive model while allowing deriving meaningful linguistic interpretations. For this, the numeric raw data is encoded into naturalistic general concept sets, defined as inactive, active, or very active. So further predictive analysis is performed using these concepts rather than the numeric values, using a specific type of calculus. Therefore, we can make use of the artificial intelligence paradigm of computing with words that allows building predictive models such as neural networks and highly expressive rule-based models that are understandable by anybody, while statistical performance is not jeopardized in comparison with black box models. In addition, we were also able to find patterns for visual and auditory processing that were overlooked in previous studies. Like the father of artificial intelligence described, the future is moving towards a more versatile, humanized AI that combines more types of intelligence at once. Our goal is to make use of all of these enhancements towards a very inclusive and free-living neuroscience using F-nears. Thank you very much. Well, that's all of my talk, so I'm happy to take questions after. Thank you.
Thank you, Javier. So our next speaker is going to be Luca Polonini from the University of Houston, who's talking about assessment of F-nears data quality at the individual and group levels.
Thank you very much, Rickson, and good morning, afternoon, and evening, everyone. So I developed this work with my excellent postdoc, Sam Montero Hernandez. Okay, so there has been a couple of excellent talks in these couple of days regarding quality control in F-nears studies, including Rickson's, of course. And our group is focused on the quality of F-nears signals. And everybody knows that, of course, both poor opto-to-scalp coupling and movement artifacts can adversely affect the quality of F-nears data. So a couple of years ago, we proposed two objective quantitative measures of quality of F-nears signals. Both are based on the strength of the cardiac pulsation that we can find in F-nears signals. One is called the scalp contact index, or SCI. The other one is the peak spectral power. And by using a combination of these two, we can clearly tell good signals, like in this case where we have strong cardiac pulsation, and the parameters are both high in this case, from a portion of signals in which both parameters are low and due to poor optical coupling, and also a portion of signals in which we have movement artifacts but that are otherwise good signals. So what we are currently doing is making this process of assessing the quality of data completely automatic to the user. So we are developing a software that loads an F-nears scan from any instrument. First, we automatically detect all the periods of interest. So we discard data, a portion of data that are irrelevant. And then we compute this image that essentially very intuitively presents the quality of the whole scan at a glance. So we have optical channels on the vertical axis, and each row of this image essentially describes the quality of the time course of each individual channel. The white rows represents good channels. The black rows represent channels that has poor optical coupling. And we can also clearly distinguish temporary movement artifacts that affect multiple channels at the same time. After this step, we summarize the quality channel by channel by computing essentially the portion of the scan that has a good quality. And at this point, the user can set a threshold for the desired quality. We set it by default at 90%. We want at least 90% of the scan to be good. And importantly, this can be exported not only for reporting purposes, but also as an input to additional steps of the processing pipeline, for example, channel pruning or excluding specific trials. This is at the individual level, but we're also automating the process at the group level. In this case, we can load an entire folder of scans. In the background, the software computes the individual assessment as explained in the previous slide. And then we produce this image that shows the quality at the group level. In this example, for instance, we have processed 207 scans as part of our NIH study. And you can clearly see that the optical probe in the frontal area has excellent quality of the data. Below the hairline, it decreases only slightly for optical channels above the hairline, but of course the lateral probe is a little bit more problematic because of hair obstruction. And this is something that investigators may want to maybe present in their publications for transparency, of course. Now, importantly, do our quality metrics actually relate and predict functional activation? So what we did to estimate this is simulating a bunch of FNIR scans in which we include all the typical components. And we varied the amplitude of the cardiac pulsation between an arbitrary unit between 0 and 1. And we also added an HRF HRF response only in 50% of the channels of this probe, so we can use the other half as a control. So we've simulated a scan with 16 optical channels, and only the top 8 one has the HRF included. And as we varied the cardiac pulsation between 0 and 1, of course, the quality of the metrics increases, and there is variability, of course, between channel and channel due to the random source of noise. But then when we average at these quality metrics at the group level, we see that the quality of the signal of the entire scan becomes 80% or greater when the cardiac pulsation is above the arbitrary unit of 0.6. This is expected. Now, we processed these simulated data with TED's toolbox, and expectedly, again, for the top 8 channels, we obtain ultimately a functional activation, statistically significant functional activation for both HPO and HBR. But interestingly, we obtain statistical significance when the cardiac pulsation has more or less the same amplitude of the cardiac pulsation, leading to high quality. And we also prove that these statistics correlating with this. So our ongoing activities, I'm very grateful to Chiara Burgarelli, Laura Pirazzoli, and all the principal investigators that are validating our tool. And we're also publishing our toolbox very soon. So watch out for that.
Thanks, Luca. So our next talk is going to be by Xinxin Fang from Northeastern University. Who's going to talk about wearable and modular FNIRS probe.
Yeah, good morning, everyone. Can you see my slides?
Yes.
Great. Okay, so I want to first thank Mari and other organizer for putting together this program. It's great to see everyone. And today I wanted to share some of the work in progress for a project we started 2 years ago on developing a wearable and modular FNIR system. The project was funded by the NIH, and we have, it's a collaboration between BU with Dr. Swathi Kiran and Dr. Marian Yuso to lead our clinical study that we're about to start. And on the technical side, my student Morris Venegas has been really the driving force, start from the beginning, help design all aspect of the hardware. We also get help from MIT student Artem Demiev, and he's currently working Google with a lot of experience in flexible circuits, and also with help from Stefan Karp. All right, so I don't want to repeat the benefit of wearable systems. The community has reached agreement that is, there's a great need for wearable FNIRS measurement for many studies that are not currently supported by a lab environment. I want to mention about modular FNIRS, and this is a concept, architecture that was kind of recently explored by the community, and you can see a lot of good papers coming out of in the past few years. Rob Cooper and co-workers have published a good review paper on this topic. So we are attracted to this concept, and I want to highlight some of the sort of potential benefit. One is being, modular systems basically explore the concept of using a repeated optical modules by interconnecting these identical modules to create flexible, reusable, reconfigurable probes. That is a very strong sort of benefit. And the other is potentially these repeated modules can be fabricated with a lower cost and easy to maintain because they're exchangeable. And also these modules typically have onboard sourcing detectors, remove the needs for fiber optics and potential energy losses. So we asked ourselves, what can we contribute? I mean, there's a lot of good works have been published. So we felt there are a few things we could, potentially add. One is if we can move this circuit into a flexible circuit that's gonna provide better conformity, better contact, comfortness for wearing it for long-term measurement. The other is, if we can automatically obtain 3D position of the optos, then we can, perform a lot of the data analysis and visualization without needing a digitization and shorten the setup time. We also found there's a lack of a general design, pipeline for explore this modular FNIR system. So we found there's a need for a software platform. So I'll start with a software platform called MoCA, Modular Opto Configuration Analyzer. It's open source MATLAB toolbox written by Morris. So, the link is there. If you wanted to be a beta tester, click on that. When we start looking at this problem, we found there's a huge design space for modular systems. First of all, you need to think about, what shape to use, what size of the module to use. What about the gap? How big of the gap you need to have? And what about the rotation? They can be symmetrical. So how do you rotate them? And within a module, you also have optos where the source is located, detector located, how many to use. Then once you have a region of interest, for example, you decide this is the area to cover, how do you tessellate? How do you connect them and route them, connecting with wires? So these are really open up a can of worms, but Morris did a great job developing this in a step-by-step approach. So we provide a descriptor for the shapes, and we provide design the modules, and also tessellate and route it, and provide some brain sensitivity, channel density, and etc. So this is a tool that's still being developed, but we felt it could be contributing to the community. For the hardware, we have a flexible circuit-based modules, and this is just a specification, and I'll show you quickly a video that Morris made. But overall, it's dual wavelengths, diamond-shaped module, and this you can connect it in a very flexible way, and with a battery that runs about 2 to 3 hours. I'm going to click on this 1-minute short video. I'll show you what this module can do. So basically, this is the module with a silicon casing, and you can bend it, and you can put on the surface of a hat conforming to the contour. And we have some hair picking holes for better positioning contact. So basically, the module can be driven by there's a master node, and then these modules can be interconnected and automatically recognize and reconfigure. You can see the optos. You can change the position, etc. And a good thing is it has the IMU on the board, so you can see the shape, 3-dimensional shape. Okay, so that's it.
Sorry, but it's
okay.
more than 6 minutes.
All right. Okay. Yeah, thank you very much. That's yeah.
Hi. Thanks, Ching Ching.
You're welcome.
So next talk, Joe Culver from Washington University at St. Louis, and he will be talking about wearable high-density diffuse optical tomography. Joe?
Just checking. Oh, I got audio. Okay. Thanks, Rickson. So as he said, we'll be talking about a wearable system that we're developing that's part of a UO1 funded project through NIBIB and the Brain Initiative. So the need for wearable is kind of obvious, but just to put it on a graph, if you were super generous about the weight of these fiber-based systems and only, like forget the console and just think about the last meter of fiber, then you're at about 7 pounds for our portable system, 21 pounds for our fixed system, and it would be like 50 pounds for a whole head. So we don't want that. We want to kind of reduce the weight by about 2 orders of magnitude down to around 2 pounds. So our inspiration for this came from many other groups who've been working on these fiberless systems for a number of years. And this is well captured by Rob Cooper's review article in 2017. And then as we just heard from Chin Chin and some other groups, there's been some work since then on medium to high density imaging arrays. And for other groups have focused on full head coverage. So what we're looking for is high density and full head coverage. And the idea was that we would replace the fiber tips with sort of smart optodes. And in doing so, we wanted to keep some things from the fiber system. Most notably, we wanted the performance to stay the same. So detectivity, dynamic range, crosstalk. And this might be more a point for discussion, but we also wanted to keep the cap fit procedure, and that uses basically the fibers to come through the hair and get down to the scalp. And the thought was that if we could keep those features from the fiber system, that we would be able to reclaim kind of the image quality that we see with the fiber-based DOT systems. So we built these smart optodes. The LED source, I would say, was fairly straightforward to build. The photodetector, for us at least, this was the challenging part, in part because there's a lot of stuff to stick into a small package. You've got the photodiode, transimpedance amplifier, and A to D. But also because keeping these power supply lines clean and keeping it low noise is kind of hard even with a larger circuit, but it gets harder when you make it small. So we put together a source, we had these modules put together a system, has 32 sources, 32 detectors. You can see the array down here at the bottom, and then this is the array on Ed's head. Ed is kind of the person who led the electronics development. And this is the system from kind of all of the systems. So there's a battery pack. The data gets streamed via FPGA and a Wi-Fi module to a laptop, so it's untethered. The wiring is kind of bigger than we want, but that was by design for this prototype, and the next prototype will work on shrinking that. So the performance of the system can be largely seen in this fall off curve, which is light fall off versus distance. And from that, you can kind of deduce the detectivity, dynamic range, and crosstalk. I'll just highlight 2 numbers. One is the detectivity is down around 12 femtowatts per millimeter squared, and the dynamic range is at 134 dB. So those numbers match up pretty well with the fiber-based systems, at least in our lab. Then we looked at pulse SNR, and this is for second nearest neighbor pair distances for every source and detector. And it stays up around 10 for most of the modules. Like we had a couple dropouts, but in general, it's above 10 dB. And then finally, we went ahead and did retinotopy with this system. And it's maybe not our best retinotopic mapping, but it's pretty good since we've really only done a couple sessions on a couple people with this so far. So, what we think is good is the performance is matching the milestones that we were looking for or aiming for. The bad is that we still need to work on the FPGA, making those boards custom and custom cables. So that's kind of like what's up next, along with building the channel count out to 144 sources and 144 detectors. So just a few seconds, I guess, or so on what we want to do with this when we get it built. And that is to work on mapping brain function with movie viewing and decoding. So we have a system that's newly built focused on kids, and we're sort of developing these protocols for imaging them while they watch things like Curious George and Moana. We then break up these clips into different pieces around 5 to 10 minutes. And then we show them multiple times in one session. And you can see, if you kind of look along the diagonal, these are the same clip being shown, and we get high correlation if the same clip's being shown, and it's a lower correlation if different clips are being shown. So if you think about this matrix, it sort of is a step into doing decoding, meaning that we could figure out which of these clips was shown. But we also have worked on sort of simpler decoding methods using just checkerboard stimuli. And so this is the results from decoding checkerboard data without block averaging. And this we can get, within around 20, 30 degrees with a 10-second window. So I'll close out with one slide, just advertising a new PhD in imaging science that we have.
Okay, thanks, Joe. So just want to remind people again that we have the discussion chat. We have the link, so please go ahead and make your questions there for the panel discussion later on. So next talk is going to be by Adam Agbert from WashU, Washington University in St. Louis. And the title of the talk is Elimination Childhood Development with High Density Diffuse Optical Tomography. Adam?
Hi, good morning, good afternoon, good evening. Good night. Can you guys see my slides okay? Can you hear me okay? Awesome. So thank you, Rickson and Mari and everyone for inviting me to participate. This is a great session, and it's really great to see all, or at least most of your faces who are active. My lab is in a bit of a transition right now, so I'm just trying to give kind of an overview of various things that we're working on. Just want to focus on this wonderful group of people down in the lower right, members of the team who did the vast majority of all the work, and of course the funding sources along the way. One big thing that we focus on in the lab is that the slides don't advance. That brain function is distributed across, the whole field of view, and we don't. We want to focus on trying to capture as much of the variability in brain function as we possibly can using the optical methods, because task-based and task-free assessments of brain function can be modulated by disease development and aging. And when you capture a larger field of view, you're able to have positive and negative controls within your data, as well as a greater sampling of what's really going on. So what we're focusing on is being able to have more of fMRI comparable image quality with these optical systems, and being able to even pair them with the classical behavior assessments of motor function, of naturalistic language, and other behaviors that are associated with autism and typical childhood development. So I'm just going to give you a quick scattershot of a few projects. One is about naturalistic language processing, where we were asking about the neural correlates of overt externalized language production, as I'm doing now, as opposed to covert language production, as we had looked at previously. So we grabbed 33 participants and used an event-related design, 5 words per little block. And you see here that in response to reading words, there's a strong activation in visual cortex, but it kind of rings the bell of the overall language network. And you do have significant activations in temporal lobe and other places. Covert verb generation, when you play words on a screen and you ask someone to come up with an associated verb for each noun, you see strong activations in left lateralized temporal lobe and prefrontal cortex. If you ask someone to overtly say these words, now they're actually saying the words out loud. Mario, who led this project, did quite a lot to make sure to train people to be able to speak without moving all their musculature and their head while they were talking. And you see really exquisite mapping of the motor cortex and auditory cortex, in addition to other aspects of the field of view. So if we contrast these maps, covert versus reading, we see the classical Broca's area. If we contrast overt versus reading, again, you see really nice distinctions of motor cortex in addition to prefrontal areas. And overt versus covert, again, you see the nice motor strip as well as other areas. And so we think that this might be interesting for BCI applications, et cetera. We can then zoom in to some of these regions that were termed significant through SPM 12. And these are just time traces, group-based time traces of the activations, showing that you can see in some areas similar activity like in visual cortex for all three paradigms, but in other areas, you see very distinctly different responses to the different paradigms for reading, covert, and overt verb generation. The second thing I want to share with you guys is our work on autism. I had a KO1 that was focused on just feasibility of this high density fiber-based array in kids with autism. So we have an initial feasibility study of 45 kids with autism, 47 typically developing kids. This is an adolescent in the cap, happily giving us data across this field of view. We utilized sensory stimulation with the idea that that variance in those maps would not be associated with autism, and lo and behold, those maps look very similar across groups. But when we look at a paradigm that has been shown with fMRI to show very distinctively different responses, looking at biological motion versus scrambled motion, there's a part of many parts of your brain, a constellation of regions really, where that pops out that someone is kind of moving around. It's not just random dots. So this first map recapitulated many areas that have been seen in the social brain. And then the second set of maps, you see the autism group has very muted response. And in the contrast between those two groups, again, we're recapitulating a number of fMRI papers that have shown strong differences in, for example, right lateralized BSTS, left lateralized dorsal prefrontal cortex. And further, that within each of these regions, the level of modulation of biological versus scrambled activity is associated with a separate behavioral assessment of social reciprocity called the SRS. So again, just replicating the work in the fMRI field. All of this was done with our NeuroDot pipeline, which I urge you to go to GitHub to download it if you like. I don't have time to go into all of it, but we used NeuroDot to now simulate, based and inspired on a lot of the work that I did with Hamid Degani over the last couple of years, looking at the promise of frequency domain high density systems, where we showed that with including phase, you're actually able to acquire sensitivity to variance that's deeper than you get with CW alone. So with a couple of grad students in the lab, we are exploring what you can gain if you use higher modulation frequencies or even multiple modulation frequencies with a whole head high density array. And one of the interesting things that come out of this is if you include the field of view in terms of voxels that have a localization error less than the point spread function of DOT at that voxel, you actually have access to more than 50% of the brain tissue than you have with CW alone. So we think that this has a lot of interesting implications moving forward. Lastly, we just got an R01. I'm happy to share where we're going to establish relationships between naturalistic brain function and behavioral assays across development, toddlers at high and low risk for autism. It's a prospective longitudinal study, so we're trying to get 100 high and low risk kids for ASD and image them at 18, 24, and 36 months. So right now we're in year 1 of 5, and I'm looking for a great postdoc. So if any of you are interested in a position or know someone that would work out, I urge you to contact me. We're utilizing these new arrays that we've developed recently for infants and toddlers. That you see we've added a motor cap here, and this just shows the field of view of these newer systems with an extraction of an fMRI, a popular parcellation scheme showing that we're able to get many traditional parcels from fMRI that cover multiple sensory motor and association areas within the brain.
Okay.
So with that, thank you very much for your time.
All right. Thanks, Adam. So last talk. Our last talk is gonna be by Stefan Karp from MGH, and he'll be talking about optimization of experimental and computational approaches for cerebral blood flow monitoring. Stefan?
Good morning. Can you see my slides?
Yes.
Well, thank you for the opportunity to speak. I'm glad to have the chance to close out this excellent mini conference. It really felt like attending the actual FNIRS conference almost. And well, I should thank Target earlier for the introduction of all the possibilities of clinical applications of blood flow monitoring. So I guess what I'm going to touch on is some of the work we're doing to make sure we maximize what we get out of it, because there's a lot of physician enthusiasm and we want to make sure we get good data so we can maintain that enthusiasm and move on to translation. So this is just a couple of pictures. I think the last group picture we took before COVID came, and then I think that was the first conference call where some people were still in the office. This is the optics group. I'm highlighting my group members, but also a lot of this work was done together with Dr. Franceschini's group, and several more people from her group were involved in the data I'm going to show. So first topic I want to mention is we really think that taking TCS blood flow measurements at longer wavelengths like 1064 nanometers can really give a leap forward in performance for brain blood flow monitoring. And the reason for this is there's multiple synergistic advantages. There's a bit lower tissue attenuation, the autocorrelation decays slower, and therefore gives better noise performance for fitting the blood flow index. But most importantly, just from a regulatory standpoint, you're allowed to put a lot more energy onto tissue, and each photon carries less energy, so the photon counts are even higher. So you could have 10 to 15 times more photons compared to measurements at 785 nanometer. So we could have 10 times the signal to noise ratio of measuring the autocorrelation function itself. So to make it less abstract, we simulated a scenario where what if we have a baseline measurement that was 10 seconds long, and then a measurement during a different state that was also 10 seconds long. Now, if the brain physiology changed between the two, what kind of change in blood flow in the brain can we detect with this pair of measurements from a statistical standpoint? So if we did a group analysis, so we simulated a number of runs of such measurement, and this plot is showing that for different wavelengths, a chance of finding a statistically significant result for a given change in flow level at 785 or 765 actually here, sorry. It's not looking that great for a short measurement. I suppose for bigger, for longer measurements, you could do better, or putting multiple fiber and so on. For 850, which is actually still, it's also used by some people in the field, things look better, but 1064 is really a whole different story, where it seems like we can reliably detect a change of 20% with just 10 seconds of measurement. So to test the best 1064 can do, we borrowed an excellent detector, a superconducting nanowire, a single photon detector for quantum opus, to take some comparative measurements. So this is from a paper recently published by us in Journal of Biomedical Optics. This is measurements on actually my own forehead at 5 and 30 millimeter separation at 785 and 1064. In both cases, the detector was the nanowire to make the detection efficiency fairly similar. I have to admit it was 90% at 1064 and probably 70-something% at 785. So what we see here is a baseline measurement followed by applying pressure on the probe. As we expect, the blood flow is reduced at the short separation. But what we really see is that there is 785 looks like it has noise. I mean, we know that it's actually blood pulsation, but it's not really clear enough to be resolved. While at 1064, you can clearly see the pulsation of blood flow and the variation across the heart cycle. And during the pressure, you can still see strong pulsatility in the long distance, indicating that's coming from somewhere beyond the scalp. And we try to push it even a bit further in a recent set of measurements. And we were able to see pulsation at 35 millimeters as well with 10 hertz data acquisition rate, which is actually double the one above, which was 5. And I'm showing also the signal from 25 to indicate that that really is the heartbeat we're seeing. It's not just noise. So in other words, just moving to 1064 with a good detector, you can definitely have pulsation resolve measurements at large enough source detector separations to effectively probe the adult brain, possibly even in older subjects. The superconducting nanowires are amazing, but they're also large and expensive. So there's additional work being done on developing array detectors that Dr. Franceschini mentioned the other day together with MIT Lincoln Lab to use a multi-pixel detector as an alternative to the superconducting nanowire. Now moving on to something that's a little bit simpler, but also potentially quite effective, is most of the work in the field has been done with what would be called homodyne DCS, where you're just looking at the fluctuations of the light due to interference in the sample. But a very simple modification is to add a reference arm where some light is split off the source and recombined with the light coming back from the sample and turn it into a heterodyne measurement. So I just showed how the actual measurement changes, and the stronger the reference arm, the closer you come to the electric field autocorrelation, which decays slower, so it gives better SNR. And in addition to that, by raising the signal level well above the interference from the environment, you can make a more robust measurement. And
sorry,
just to
Stefan.
point out,
finish talking. say
so
your
this can give twice the SNR for blood flow measurement, as recently published. And finally, I wanted to point out that there's definitely extracerebral physiology influence, as also confirmed by the St. Lawrence group recently. The hypercapnia actually shows a significant systemic response. And what I wanted to show here is that one possibility is to use Monte Carlo simulations. And
Stefan, you're way over.
Okay.
Thank you very much.
Well, then that's that.
Okay. So we have a couple of questions here. I'll try to go through most of them. So first, Ted Hupper. So there are a couple of questions regarding short channel separations and how to deal with that in the library. I'll try to combine two of them. That's about the same topic. So how do you actually combine the short separation measurement for functional connectivity? Does it operate differently than the task-based GLM analysis? And the second question is, basically, what happens with the regressor if the regressors are noisy, right? So do you recommend principal components as regressors?
Sure. So the paper by my postdoc Hendrik Santosa actually looked at a lot of these issues of different ways to pre-process the short separation, whether it's doing a PCA and using the components or using the data as is and so on. One of the things that we do in the toolbox that we recommended from that paper was actually you take your short separation, you do a principal component, and then you use the components as regressors. We use all the components. We don't, even though the later ones are just noise, we still found it better to include all of them and deal with it as regressors. We also, in the context of noisy data, particularly motion artifacts that affect the short separation, we use robust statistical methods, so outlier rejection, both on the short separation and on the actual data itself. So it's a multivariate statistical outlier method. In the context of the resting state connectivity and how you use short separation in that context, it's something we're still working on. We have a grad student from Heather Bordfeld's lab who's actually in the process of writing up a paper to compare different methods. We were comparing methods like partial correlation, Granger's causality, versus using short separation as a pre-filtering and so on. What it actually looks like is partial correlation with the short separation as part of what you're partialing out is probably the best way. However, one of the challenges of that is how do you define outliers and motion artifacts? Because when you have so many multivariate channels of data going in and they all have noise, how do you downweight outliers and stuff. And so we're finding our conventional methods are actually overcorrecting the stats in that case. And so we're still working on some of those issues. You're on mute, Rickson.
Thank you very much. So we do have a couple of questions with software integration with the new as-near format. And so Luca, one question, it would be possible to save the data quality metric back to the as-near file so that it could easily be used by other toolboxes?
Absolutely. We're already working on that. And it will be, compatible with all the formats, on all the standardized formats to the maximum extent possible, so they can be used in any preferred pipeline or software tools.
Great. Another question for Javier about computational intelligence. So it's a question that I have actually. Do you think that computational intelligence, if you use computational intelligence to both pre-process the data and analyze the activation, that may lead to overfitting of the data? How do you?
Yeah, good question, Rickson. Thanks a lot for the well-conduced session. So you have worked quite well. Yeah, that question is actually a very important one. Obviously, there is, when you use any ML or AI model, there is always the risk of including some residual variation in the underlying model structure, which is quite bad because we are not modeling exactly the phenomena that we are looking after. So, I mean, two suggestions is, one is like clean your data quite well before applying this model using, for instance, Professor Harper toolbox using analysis and so on. And in the model, use a lot of mechanisms that constrain your model to become too complex. A lot of dropout layers if you're dealing with a neural network, or strong regularization in every single, let's say, cost function that you might add there. And then that will actually simplify or push the model some limits that it won't allow to go into a complexity that it's modeling absolutely every noise that's included into the data. But I would say that at least in this field, in the experience I had working with these models in NIRS, is sometimes you're limited by the statistical power of your sample. So I won't expect to see in this area like it's normally called in AI conference and so on, 95, 99% accuracy. So getting, let's say a sensitivity and specificity around 70, 80, that's actually quite good. I mean, for a model, which is actually to model from just the signals, something that is capturing the phenomena. So yeah, absolutely though. That's kind of the issue, right? In when you are using these models. I hope that did answer your question. So.
Yeah, thank you. Questions for Joe Culver, also related to the design of the system or to the detection of the system. So one question related to how robust against hair is your new wearable system? It seems your probes are placed in the occipital hairy region. And kind of the same topic, which detector do you use? If these are the APDs, aren't you worried about high voltage?
So they're photodiodes. They're not APDs. And I'll try and find the part number and throw it in the chat. And yeah, it's over the hairy area. And I think, so far we don't actually have a ton of experience with it. We've put it on a couple people, but it seems to work fine. We kind of designed it from the beginning to mimic the fiber tips. So I don't know if anybody remembers what the inside of the cap looked like, but it looks like almost identical to what the inside of a fiber-based cap would look like.
Can I add questions to that? So are you concerned about heat or weight, or right now you think?
Yeah, we're tracking all of those things. Heat, maybe less so, but definitely weight. I mean, if, we started from the photodiode modules and kind of worked out, and then for sure that the wiring rig ended up a lot bigger than we thought. And so I think for it to be usable, that weight has to come down. I mean, the Gower Labs thing looks awesome, and they've solved a lot of the ergonomic industrial design parts that we have yet to fix or yet to address. I think, you know, it does come down to power, weight, and data throughput also is kind of challenging with if you want to do Wi-Fi with really high streaming rates, then that ends up taking lots of power. And so, yeah, solve those things.
Okay, great. So one question for Chin Chain. Which kind of microcontroller are you using for the modules, and whether each module has its own controller? And if I may add to that question, how does that impact temporal resolution?
So we have the ARM Cortex M4 for each of the module. Yeah, each one has a microcontroller, and the master node has a Cortex M7. It's a little bit beefier version. In terms of speed, the sampling rate is like 300 hertz per channel. I mean, we basically, in order for us to get like spatial measurement, we have to develop this sort of called multiplexing groups, and we have to turn on each subsection. So that is kind of a constraint. And right now, our full head probe projected is about 5 hertz, but we have some tricks to improve it, probably up to 12 hertz.
Great. Okay, so one question for Adam. So over language production changes the PCO2 in the blood, which strongly affects brain hemodynamics. Did you measure PCO2?
No, we did not directly measure PCO2. So we're planning on just releasing all of this data, since there's a lot of it to be explored, so that the community can have at it with all of the various questions.
Great. One question for Stefan. Should we, that's a great question. Should we all move to heterodyne DCS?
Well, that's what I was trying to say. I mean, it's okay. There's requirements on the laser stability. And evaluate, I think we found some lasers were too noisy. But it's worth looking into. That's what I would say.
Great question. Another question for Ted related to the EEG. So right now, what level of EEG analysis can be performed? Example, microstates or FFT?
Yeah, so the EEG, and it also covers MEG within the toolbox, are things that we're actively adding. Most of my research that uses EEG actually focuses on, we use multimodal NIRS EEG during balance and gait and stuff like that. So the tools that are in it are basically ones that we've used in our research, but we currently have bandpass filtering, principal and independent component analysis for artifact rejection like eye blinks and so on, spectral analysis, connectivity analysis, and image reconstruction. And what we've been kind of focusing on the most is multimodal methods. So for example, taking EEG time course with a concurrent NIRS time course and doing things like canonical correlation to try to denoise the data. So you're removing components that are only in EEG and not appearing in NIRS, and kind of more statistical fusion methods. So the EEG tools are somewhat sparse, but we've really been focusing on these kind of novel multimodal tools within the toolbox.
Okay. Another question for Luca as well. Can you elaborate a bit more on the difference between motion artifact and pure optical coupling?
Yes, absolutely. So essentially, by using a combination of the SCI and the PSP values, and one is in the temporal domain, the other one is in the frequency domain, we're able to distinguish a poorly optically coupled signal, which has both SCI and PSP at the very low values, compared to a movement artifact in which the SCI parameter stays really high, but only the PSP value is low. So essentially, by doing some sort of a logical end between the two between the two values and looking at them together, we're able to separate out these two cases quite reliably.
And I guess last question, Joe, really interesting system design. Is there a paper on the way?
We don't like papers. So, I mean, yes, there will be, but actually, I'll tell you that we're trying to get the next iteration of it with where we've improved some of the industrial design stuff before we publish.
Okay, thanks. So I guess we are right on time. There are a few other questions on the chat, so I encourage all the presenters to visit the chat and answer the questions that haven't been done here. And I guess I'll pass the word to Mari.
Thank you, Rickson, for sharing all by yourself. And thank you, everybody. I want to apologize with all the speakers. I stopped because they were going over 6 minutes instead of 5. And we will post today videos in the webpage, and we will leave it available free for everybody for next 1 or 2 days, but then it will be restricted to only members. And the question will be always there, and we hope everybody keep asking questions and such. So I'm very happy how it went. I was a little bit scared, but that everything crash or people get bored, but it seems this format worked really well for online. I just hope next year we will all be there for in person for the real meeting. If not, we will have to think about some online format that doesn't kill us, staying many hours in front of a Zoom computer. So just very briefly, some statistics. We had 635 registration and 51 speakers. The attendee during the Zoom session were lower than the registrations, but still quite high. And the registrations across the world, there were a lot from the US, but also a lot from Asia and Europe, and from many other countries. This shows that our field is expanding, and many people are interested kind of everywhere. This is some other statistics. I'm not going through all the details. We are 50-50 male and female. There is a lot of PhD, but there is also a lot of bachelor and masters combined. The age groups, the young one are the most, so that's very exciting. And so it's a growing field, and that's really good. And yeah, we're mostly white or Asian, but hopefully we will increase also our ethnicity and more broadly. So let me conclude by thanking Felipe that helped me with the webpage. David also helped me with the video. My postdoc, Juan Sonwo, that was helping me turn off all the microphones. And the program committee and moderators that saved me in many occasions by taking the leads. And of course, the speaker and attendee. Claire, you want to say bye to everybody?
Yeah, what I want to say mostly is a really huge thank you to Mari. So it was her idea to make sure that we had some type of virtual event to make sure that we could meet as a community this year. So I think we should just all do a round of applause for Mari. A really good job, well done. And thank you to the programme committee for making sure that this happened. And just to echo Mari's words, that we really hope we can see you all in person soon, and hopefully in Boston next autumn. Thanks everyone for the amazing contributions as well.
Bye everybody.
Thank you.
Bye. Bye. Bye.